manifolds with boundaries. So far we have looked at manifolds without boundaries. We have an idea of what a manifold should be, and we do have an idea what a boundary of a space of something should be, namely the points, if they belong to the space, that are the last ones before I fall off, right? So far our manifolds have not had any boundary points as, for example, S1. If I live on this as a one-dimensional ant, I can walk on in whatever direction for as long as I want. As long as I stay on S1, I'm not falling off. If I live on the surface of our planet, simplified, 2D, I can stay on the Earth and not fall off. No boundary. If, however, I'm a flat earther and I believe I live on the desk, then I should be careful to not fall off, because now I do have a boundary. So, question, how do I define boundary of a manifold? You could think as a first approach, or maybe you stop and think for a moment. But what you could think is, well, we have a definition for boundary points for topological spaces, or for subsets of topological spaces. And our manifold, so far we looked at embedded in a topological space, so why don't I just use that? But, so what is this? Recall, a point is a boundary point of a subset in a topological space if in every neighborhood around this point there are points both that belong to the space and points that do not belong to the space. But now if, for example, I look at S2 as embedded in R3, well, as a subset topologically in Euclidean topology, each point is a boundary point, because around each point I have neighborhoods. For all neighborhoods, there are points that are in the sphere and that are outside the sphere. So that's not quite the right definition. I really want to keep it, I'm staying in the manifold. So what's the difference between such a point here in the boundary and the points we have had in the manifold so far? Well, it's that the neighborhood looks different, right? So all these points have charts. That's how we defined manifolds so far, that are diffeomorphic to a neighborhood in, well, here R2, and the Euclidean space with the same dimension, or here R1. So, but here this neighborhood looks different. Namely, it looks like this. So a better, more natural way, and the one that works, is instead of taking neighborhoods to be diffeomorphic to something in Rn, we take neighborhoods to be diffeomorphic to something that looks like this. And this is, well, in this case, also two-dimensional. Instead of R2, taking the upper half sphere. So H2. And now for points on the boundary, we can take a neighborhood here and take a chart of parametrization, and for points in the inside, everything looks the same because we're in the upper half of the half space. So there's a definition, which is exactly that. A subset X of Rn is a k-dimensional manifold with boundary, okay, with boundary if every point of X possesses a neighborhood, that is diffeomorphic to an open set